Hello, how are you doing? This is Mike here, and we in this video are going to talk about how to graph a polynomial. So we are going to bring together two different topics. We're going to talk about first the multiplicity of a zero, and we're going to combine that with our leading term analysis. So in order for us to graph this polynomial, we're not going to graph every single point of it. We want to graph some critical values, some critical areas about this polynomial. So first of all, with our critical values, we know that every zero is going to be a critical value. So we are going to graph the zeros. That is important. Is it important for us to determine every point from one zero to another? Absolutely not. For right now, all we want to do is get the basics of how to determine the zeros. But specifically, we're going to have to determine the action at those zeros. So we're going to have to talk about the action of those zeros, whether or not the graph crosses or whether the graph just touches at those zeros. And the next thing that we're going to want to talk about is leading term, not end term, leading term behavior, which will give us what happens at positive and negative infinity. So I'm going to start using the term positive infinity and negative infinity. In terms of our graphs on our domain, positive infinity exists to the far right. Negative infinity exists to the far left. So as we talk about leading term behavior, this is synonymous with end term behavior, or it's synonymous with leading term analysis. Each one of those discusses what happens as we approach positive infinity as we approach negative infinity, what happens on both sides. So we have already discussed how to determine these two categories in our last video series. So if you need to, go back and review those specifics so that way you get caught up. Let us talk about one specific rule. Well, not really a rule, but let's just talk about a characteristic of a polynomial. So a characteristic, I think that's the correct way, characteristic of a polynomial. So actually there's a couple now, but so maybe we should abbreviate that and say characteristics of a polynomial. The first thing that I always like to talk about and reinforce is the domain of all, again there's that absolute, all polynomials, which I'm going to abbreviate polys, is all real numbers. So we're going to learn eventually that this indicates that a polynomial is a type of function that's continuous. There are no breaks, there are no holes, and there are no asymptotes, but we haven't really defined those terms yet. But I wanted to give you an interlude or a prelude of what to expect later on. And we also know that the degree of the polynomial is indicated by the largest exponent, of the x values. So if there are multiple x values, you're going to learn that the degree, or actually we already know, the degree of that polynomial is indicated by the largest exponent. So for example, if I give you f of x equals to 3x to the fifth minus 4x cubed minus 2x plus 1. We recognize here that the degree of this polynomial is a fifth degree polynomial, fifth degree poly. So once we determine the degree, that degree can actually tell us a little bit more about our graph. So we are going to define the degree as the largest. We define the degree of the polynomial as the largest exponential value. Therefore, the degree will indicate the number of possible real zeros. So we could say the degree will indicate the total real zeros, but we could also say it will indicate the total zeros, because we're going to learn that the zeros of a polynomial can be both real and imaginary. Imaginary. And when you add these two together, that will give you the degree. That's a horrible bracket. There we go. That will give you the degree of the polynomial. So the real zeros plus the imaginary zeros will give you the degree of the polynomial. But ultimately, if you have a degree of 5, for example, in this example, we have a degree of 5, we could have at most 5 real zeros. We could have 3 real zeros and 2 imaginaries. We could have 1 real zero and 4 imaginaries, but we'll talk about the different combinations of real and imaginary zeros we can have, but we can have at most 5 real zeros. So then they're going to be a little bit more explicative, and they're going to tell you that there will be a possible of, we could call this a possible of, there's a possible, we'll call this degree minus 1, degree minus 1 turns or curves in our graph. And these turns or curves are usually defined in terms of maxes and mins. Maxes and mins. So let's look at an example. Let's look at an example here. So if we give you f of x is equal to x squared. X squared, oops. This gives us a parabola opening up like such. So here we recognize that this was an even exponent, so the multiplicity of the 0 is even, therefore it's going to touch. But notice there is one turn. There is one turn in the graph, which is synonymous with a max or a min. But in this circumstance, it's a min. So notice here that if we take the degree and we subtract 1, that gives us one possible max or min, and that's going to be at most. So we're never going to exceed this value. So if we look at that example that we had before with that x to the 5th, we could have 5 minus 1, 4 total turns or curves in the graph, but we're never going to have more than 4. But we could have less. We could have 4, we could have 3, we could have 2 or 1. However, the most important thing we want to recognize here, I would say, is the number of zeros, Because if we know the total number of possible zeros, the turns will fall into place right thereafter. So again, remember that if you have a nth degree polynomial, there are at most n zeros. There are at most n real zeros as well.